In this lesson, we are going to focus on graphing exponential functions. A function is considered to be an exponential function if the independent variable is a power. So in this equation here, our independent variable is x, and you could see it is in that power position or the exponent position. The a is a constant, our coefficient, and the a is going to represent our y-intercept in our graph. The B is what's called the base, and the base is what's going to change the shape or curve of our exponential graph. Now, if it is a growth function, then that means the base is going to be larger than 1. So as x gets larger and larger and larger, the value of y gets larger and larger and larger. If b is between 0 and 1, that means as x gets larger and larger and larger, the value of the function is going to get smaller. That represents decay. So we're going to be exploring both growth and decay in this lesson. So let's start by looking at how to graph the exponential function y equals 3 to the x. Now, I chose a handful of different values around the origin to start with. In the past, you may have focused primarily on these 5, substituting in -2, -1, 0, 1, and 2. And for your x position or x values, we're going to look at a larger group of numbers here, just again to explore our new shape. All right, so looking at the one that is already worked out for you. What happens if -3 is your input for x? Well, if I have y equals 3 raised to the x, this is 3 raised to the -3. Now, anytime you have a negative exponent, you're going to bring the base to the denominator of the fraction to make that exponent positive. So now you're left with 3 cubed, which is 27. So when -3 was my input, my y value was 1 over 27, which is going to leave me with the ordered pair, -3, 1 over 27. So that's going to be very, very, very small. So when I go to the left 3, I'm going to be just about here. All right, what happens when I plug -2 in? Repeating that same process. So now I'm going to have y is equal to 3 raised to the exponent -2. And I'm going to go through the same process. I'm going to take the base and I'm going to move it to the denominator. So that's going to give me 1 over 3 squared. And I know that 3 squared is 9, so I end up with 1/9 as my output. So when I have -2 as an input, I have positive 1/9 as an output. So -2, 1/9 is the ordered pair that I'm going to look at here. So -2, 1/9, that is larger than 1 over 27. It still is very, very small. All right, what happens when we use -1 as an input? Well, that gives me y is equal to 3 raised to the negative first. Making that exponent positive, I'm going to put the base in the denominator. So that gives me 1/3 as an output. So that means, again, my ordered pair is going to be -1 and 1/3. So as you can see, I'm still quite a distance away from my 1 value. All right, what happens when y or x is 0? So if I have y is equal to 3 raised to the 0, hopefully you remember that any number raised to the 0 is equal to 1. So that means when 0 was my input, 1 is going to be my output. So the ordered pair here is 0, 1. All right, now, originally the function that I gave you was y is equal to a times b to the x. And if you look at the function that we're actually graphing here, there is no a value, which means it's represented by 1. And I'm doing 3 as my base and x as my exponent. So if I look at this one, it's saying the value of a, or the leading coefficient, or the constant, is 1. And that means that my y-intercept is going to be at 1. So 0, 1 is going to be the y-intercept. Now, when I just used 0 as my input, I got 1 as my output. So you can see that the graph is going to cross at that 0, 1 point. All right, let's keep going. When I have 1 as my input, I have 3 to the first. So that means my output's going to be 3. So 1, 3 is my ordered pair. It's finally going to get a little bit larger here. 2 is my input. I have y equals 3 squared, and we all know that 3 squared is 9. So 2, 9 is my ordered pair. And if I plug 3 in, holy smokes, this is going to be 3 cubed. 3 cubed is 27, and we know that that is way, way, way off our graph. So it would be, this is just a guess, something like that. So now if I'm actually going to connect these points, you can see it's increasing here. And as the value of my input got smaller and smaller and smaller, the output got smaller and smaller as well. Now, since A was 1, again, that told me my y-intercept was 0, 1. Since my base was 3, we said anytime the base is larger than 1, it's going to represent growth. So the question over here said, is it growth or decay? Growth is going to be the correct answer. And again, that's because my base is 3. And since 3 is greater than 1, this is representing a growth model. So as the x gets larger and larger and larger, the y is going to increase what they say exponentially. All right, so let's consider this situation. What y value can the function y equals 3 to the x never be equal to or less than? Well, as my x's got larger and larger and larger, you could see that my graph increased exponentially. And as my x's got smaller and smaller and smaller, the value in the denominator increased where my value in the numerator did not change. So this value or curve here is getting smaller and smaller and smaller, but it actually never touches that x-axis. So this x-axis here is represented by y equals 0. And what we're going to say now is that y equals 0 is a horizontal asymptote. And we talked about that when we were graphing rational functions. So I have a horizontal asymptote at y is equal to 0. All right, domain. Well, you can see I never picked my pencil up when I drew my graph, so the domain is always going to be negative infinity to positive infinity for exponential curves. My range now, the y values are limited by that horizontal asymptote. I am going to use a parenthesis for the 0 because it does not touch it, but it's going to go on infinitely in that positive direction. All right, let's look at a second example. In this problem, again, my a value or leading coefficient is 1. So since my leading coefficient here is 1, that means without even plugging any points in, I know that my y-intercept should be at 0, 1. Well, let's check that out. If I plug 0 in for my x, that means that I'm going to have y is equal to 1/3 raised to the 0, and anything raised to the 0 is going to be 1. So I am correct with the fact that my y-intercept is going to be 0, 1. Let's analyze the base before we start. If I have a 1/3 as my base, is that growth or decay? Well, by definition, if my base is larger than 1, that represents growth. Well, if we think about what that value is, we all know that 1/3 is not larger than 1. However, 1/3, my base here, is bigger than 0 and less than 1. So that means that this is going to represent a decay. So it's going to be a decay function. And that again is because the base is between 0 and 1. So growth means that my curve is going to increase from left to right. Decay means that my curve is going to decrease from left to right. As the x's get larger and larger, the y values get smaller and smaller and smaller. All right, so let's see if my graph does look like a decay model. Let's plug -3 in. All right, so now I have my y equal to 1/3 raised to the -3rd. Now, that's a little confusing there. If we think about it, if you have 1/3 and I'm raising it to the negative third, really what that's doing is saying that I have 1 to the negative third and 3 to the negative third. In order to make those exponents positive, I'm going to move that base 1 to the denominator, and I'm going to move the base 3 to the numerator. So really what you're doing again is interchanging these two bases. Now, we all know 3 cubed is 27, 1 cubed is 1. So what I did with this negative exponent here is I actually took the reciprocal of my output. So 27 is going to be the value that I end up with when I raise 1/3 to negative 3. So my output here is going to be 27, and that gives me negative 3, positive 27 as my point. All right, let's keep going. If I have negative 2 as an input, now that means I have my y that is equal to 1/3 to the negative second. Again, that's going to take the reciprocal of my fraction, so that is going to be the same thing as taking 3 and squaring it. Does that make sense? Well, let's take a look at that real quick down here. If I have 1/3 and I'm raising it to the negative second, I'm really taking 1 to the negative second and 3 to the negative second, so that base 3 goes on the top, base 1 goes on the bottom, and 3 squared is 9. So 9 is my output, and I have negative 2, 9 as my ordered pair. All right, if negative 1 is my input, I have positive 1/3, raising it to the negative first. Again, that means I'm going to take the reciprocal. The reciprocal of 1/3 is going to be 3. So that means my ordered pair is going to be negative 1, 3. All right, when I plug 1 in for my x, I have y is equal to 1/3 to the first. That does not change the value of my base, so 1/3 is going to be my output. If I raise it to the second, that means that I'm going to have 1/3 times 1/3, which is 1/9. So now you can see here the values are getting smaller and smaller and smaller. Raising that base to the third is going to be 1/27. Now, what I want you to notice here is how these ordered pairs relate. Well, if you look at your outputs here, I have a 27 as an output when I had negative 3 as an input. And when I had positive 3 as an input, I had 1/27 as an output. But negative 2 as an input gave me 9. Positive 2, oops, this was supposed to be a positive 2. Apologize for that. Positive 2 for an input gave me 1/9. Negative 1 gave me 3. Positive 1 gave me 1/3. So what it's doing again is anytime I'm plugging a negative in for my exponent, I am taking the reciprocal of that fraction. All right, so let's plot some points, see what it looks like. So negative 3, 27 is way, way off the graph. However, I can make a little estimation here. Let's say I put it up here. If I put negative 2 in, I got 9. When I plug negative 1 in, I got 3. 1 gave me, or 0 gave me 1. 1 gave me 1/3. 2 gave me 1/9. 3 gave me 1/27. So again, it's going to look something like this. Gets closer and closer and closer to what? It's going to get closer and closer to 0. It does look like the decay model that I was hoping for. Exponential decay. As the x gets larger and larger, the value of y gets smaller. Again, this is going to be my horizontal asymptote. The value is never going to actually touch 0. So we said it was a decay. It's never going to equal 0. So that gives me a horizontal asymptote at y equals 0. Domain, again, you never picked your pencil up. It's continuous, negative infinity to positive infinity. And the range, again, is going to go from 0 to positive infinity. All right, this one is kind of a jump in difficulty here because what we're doing now is looking at transformations of our basic function. And the basic function that we're working with is a y equals 2x. So what I thought we could do is come up with an XY chart, some nice ordered pairs, and then we're going to shift our curve. So when I plug -2 in, I have y equals 2 to the -2nd. 2 to the -2nd is going to give me 1/4. All right, when I plug -1 in, that gives me 2 to the -1st. 2 to the -1st is going to give me 1/2. When I plug 0 in, again, anything to the 0 is 1. When I plug 1 in, we all know 2 to the 1st is going to give me 2. And plugging 2 in, 2 to the 2nd should give me 4. So again, if you look at these, we analyzed these a little bit when the last one. Here I have a negative value that I plugged in. I got 1/4. When I had a positive 2 that I plugged in, I got a positive 4. -1 gave me 1/2. Positive 1 gave me 2. All right, so what happens now? I've got these ordered pairs, and we're going to talk a little bit about these transformations. Well, if you look at x minus 2, that means that my curve is actually going to be shifted to the right 2. So I am going to be adding 1 onto all of my x values. Okay, let's see if we just look at that y transformation. If I have 2 to the x and I'm adding 3, this means that because it's addition, I'm going to go up 3. So again, here I went right 1. So I was going to add 1 to all my x values. I'm going to go up 3. So now I'm going to add 3 to all of my y values. Add 1 to the x's, add 3 to the y's. So let's look at these transformations. Now, it's telling me here that I am going to shift my graph to the right one. So that means each one of these x inputs, I am going to add 1. So the -2, if I add 1, that's going to get me to a -1. My -1, if I add 1, that means it's going to be at 0. 0, when I add 1, I'm at 1. 1, if I add 1, that brings me to 2. 2, if I add 1, that's going to bring me to 3. All right, let's talk about my y values. My y values here with this +3, again, said my graph is going up 3. So that means for each of my y values that I found by substituting those x's in, those inputs, I am going to add 3. So I have 1/4. If I add 3, that's going to be 3 1/4. When I had 1/2 and I added 3, I have 3 1/2. 1 and I add 3, it's giving me 4. 2, I add 3, it's going to give me a 5. And 4, I add 3 is going to give me a 7. So again, when I looked at my new x values from here to here for my x values, what did I do? I added 1. And what about my y values? From here to here, I added 3. So what does that mean? That means that my original graph is going to go to the right 1 and up 3. Now, if it would help you to graph that original curve on your x and y axis so you can visualize the shift, feel free to do that. I'm going to plot the points that I started off with or ended up with here. I have -1 and 3 1/4. I have 0, 3 1/2. I have 1, 4. I have 2, 5. And I have 3, 7. It's starting to get larger and larger and larger. So my graph is actually going to look like this. Now I need to figure out what it doesn't touch. Well, my original graph, if I were to plot points for that y equals 2 to the x, it would look something like this. Again, that's a very loose sketch with my y-intercept being 0, 1. So what did I do? I shifted that to the right one. So again, that would mean that this would be to the right one. So now it looks like this. And then what did I do? I moved it up 3. So this point's going to go up 1, 2, 3. So it's going to look something like that. So if my original horizontal asymptote was at 0, my new horizontal asymptote went up 3. So 0 plus 3 means that my horizontal asymptote is now going to be at y equals 3. So if I finish my curve, even though I didn't plug in anything less than -2, it's going to go closer and closer and closer and closer. And again, level off at 3. So why is it a growth? Well, the initial base here was 2. And we know that if the base, or b, is greater than 1, then it represents a growth model. So since 2 is larger than 1, I'm looking at exponential growth. All right, what y value can the function never equal or be less than? We already talked about that. That is going to be 3. So I'm going to have a horizontal asymptote at y equals 3. Domain, never picked your pencil up, negative infinity to positive infinity. And the range, again, is going to be everything over 3. Now, you might have looked at this saying, looking at that adding 1 and then adding 3 seems like maybe not a method that I would follow. You can do all of this in one step if you would rather. Let's try that. I'm going to erase this just so we have a little bit of space. And let's try this for maybe 1 or 2 numbers. Let's say instead, I'm just going to use 0 as my input. If I use 0 as my input. So if x is equal to 0 and I choose to plug this in all at the same time, that's going to be 0 minus 1 plus 3. This is going to be 2 to the negative first plus 3, which is 1/2, plus 3, which is going to give me 3 1/2. Now, do we see that ordered pair? We sure do. Here is my 0, 3/2. If I were to repeat that same process with my 1, because it's saying, well, if I plug 1 in, do I get 4? That is a great question. Let's take a look at that. If I were to plug 1 into my original function, that would give me y equals 2. I'm going to plug 1 in, 1 minus 1, adding 3. So 1 minus 1 would give me 0. Anything to the 0 is 1, and 1 plus 3 equals 4. So here you go. When I plugged 1 in, I did get 4 as an output. So that last thing that I'm talking about, that last method, is it quicker? It may be for you, but I did choose to go through the original process because I wanted to show you how when you move each point to the right one and each point up 3, it does get you to this final position, this final graph. But if you're like, hey, that's for the birds, I'd rather just plug everything in at one time, you can follow that process as well.